You are not witnessing an explosion. You are standing after it. 3I. Atlas has already passed through the most dangerous region of the solar system. It has traveled close to the Sun, where many small bodies are torn apart, vaporized, or erased entirely. But 3I Atlas does not break. It does not vanish. And when it emerges again, what remains is not silence, but data. For the first time in history, an interstellar object is tracked continuously by ground-based telescopes, space-based observatories, and even from the surface of another planet. Not for a brief window, not by chance, but across a sustained, deliberate observational campaign. Along that journey, 3I Atlas leaves behind the clearest chemical signature ever recorded from a visitor that originates between the stars. Not ambiguous, not speculative. Quiet measurements, consistent and precise. This is not a story about aliens. This is a story about what interstellar space actually does to matter. When there is no star to provide warmth, no stable orbit to offer protection, and time stretches across millions of years. 3I Atlas carries no message, but it carries something more valuable. A rare experimental lesson that astronomy has been waiting decades to receive. When 3I Atlas moves behind the Sun, it does not disappear in a dramatic way. There is no flash, no sudden loss, no moment of visible collapse. It simply enters a region where observation becomes impossible. From Earth, the Sun overwhelms everything nearby. Its light saturates detectors, blinds cameras, and erases faint objects from view. This is not a failure of technology. It is a boundary written into physics itself. For weeks, sometimes months, objects like 3I Atlas pass through what astronomers quietly call the solar exclusion zone. Instruments are still operating. Telescopes are still pointed with care. But the data stream goes silent. The object is there, following its trajectory with perfect indifference, while humanity temporarily loses the ability to watch. This is the obscured phase, the hidden interval, a stretch of time when prediction replaces confirmation. Orbital mechanics tell you where 3I Atlas should be. Gravity does not stop working just because you cannot see its effects directly. The equations continue to run calmly, without concern for human visibility. But certainty changes character during this phase. It becomes mathematical rather than observational. You know where the object must be, but you cannot verify what is happening to it. That distinction matters, because near the Sun, small bodies are tested. Thermal stress rises rapidly. Volatile materials sublimate. Internal pressure can build. Some comets fragment here. Others shed mass so violently that their identity is altered forever. History provides many examples. Some objects fail quietly, some fail catastrophically, some never reappear. So when 3I Atlas enters solar conjunction, astronomy enters a familiar but uncomfortable psychological state. You are not watching a mystery unfold. You are waiting to see whether your understanding holds. This waiting has a human dimension that is easy to overlook. Astronomers do not stop working during obscuration. They refine models. They recheck assumptions. They calculate thermal loads, spin states, expected mass loss. But all of this work is provisional. It exists in a space between knowledge and confirmation. Silence is also a kind of data. During this interval, nothing new arrives. No brightness measurements, no spectra, no images, just the quiet continuation of time. In public narratives, this absence is often framed as suspense. In scientific practice, it is something more restrained. It is a pause in measurement, not a pause in reality. Space rarely gives us simple answers. The Sun is not merely a source of light. It is a physical environment. At close distances, solar radiation heats surfaces unevenly. Shadows and rotations matter. Material properties matter. An object formed around another star with a different radiation history may respond in unfamiliar ways. This is especially true for interstellar visitors whose internal structure has never been tested inside a system like ours. For 3I Atlas, this passage is critical. It is the moment when its long interstellar history meets a new thermal regime. For millions of years, it has traveled in deep cold, exposed only to sparse starlight and cosmic radiation. Now, briefly, it is immersed in intense solar energy. This contrast is extreme. The physics is well understood in principle, but the outcome for a specific object is never guaranteed. During obscuration, you do not know whether 3I Atlas is shedding material gently or violently. You do not know whether jets are forming, whether internal layers are exposed, or whether structural weakness is developing. You only know that whatever happens here will shape what you observe later. Numbers whisper more than they speak. When the object finally emerges from behind the sun, astronomers do not look first for spectacle. They look for continuity. Is it where it should be? Is the brightness consistent with expectations? Has the trajectory changed? These are quiet questions, answered by careful comparison between prediction and measurement. If the object fails to reappear, that absence itself becomes a result. If it returns intact, that too is information. In the case of 3I Atlas, the waiting ends without drama. It re-emerges, the position matches the orbit, the signal is there, the object is still coherent. This alone is significant. Survival through perihelion is not guaranteed, especially for small bodies with unknown internal structure. What matters psychologically is not relief, but recalibration. The models did not break, the object did not behave wildly. The universe once again aligns with patient prediction rather than surprise. This moment sets the tone for everything that follows. If 3I Atlas had fragmented, the story would end here, replaced by debris analysis and statistical inference. But because it survives, it becomes something rarer, a continuing experiment. From this point forward, every new measurement carries the imprint of what happened during the hidden phase. Changes in brightness, chemistry, or motion are interpreted as consequences of solar exposure. The obscured interval becomes the unseen cause behind visible effects. There is a subtle humility in this process. You accept that some transformations occur beyond observation. You reconstruct them indirectly from what remains. This is how much of astronomy works, not through continuous watching, but through careful inference across gaps. The disappearance of 3I Atlas behind the sun is not a failure of vision. It is a reminder of scale. The universe does not arrange itself for uninterrupted measurement. It offers windows, and it closes them. And when observation resumes, you do not pick up where you left off. You begin again, informed by the quiet certainty that something important happened while you were not looking. When 3I Atlas slips into the sun's glare, it vanishes from ordinary sight, but it does not vanish from all vision. Some instruments are designed not to look at the sun, but to look past it. They operate in conditions where brightness would normally erase detail. These are the quiet observers that continue working when most eyes must turn away. A coronagraph is one of those instruments. At its core, it does something conceptually simple. It blocks the sun itself. By placing an artificial occulting disk in front of the optical path, a coronagraph creates a controlled shadow, allowing faint nearby objects to emerge from the overwhelming glare. This technique mimics a natural solar eclipse, but with precision and repetition that nature cannot provide on demand. Artificial eclipses change the rules of observation. Instead of waiting for the moon to align perfectly with the sun, engineers create alignment inside the instrument. Light from the solar disk is suppressed, scattered light is reduced, and the surrounding space becomes visible again. This is not complete darkness. It is a carefully managed dimming, enough to reveal structure without pretending the sun is not there. For satellites equipped with coronagraphs, the sun becomes something that can be handled rather than avoided. Space-based platforms have an advantage here. They do not contend with Earth's atmosphere, which scatters sunlight and introduces noise. In orbit, the optical environment is cleaner, more predictable, and more forgiving for delicate measurements. This is why some satellites continue to see when ground-based telescopes cannot. It is not that they see better in a general sense. It is that they see differently. Space rarely gives us simple answers. These instruments are not looking for dramatic images. They are measuring gradients, faint emissions, subtle changes in brightness. When an interstellar object passes near the Sun, coronagraphs can detect how its surrounding material interacts with solar radiation. They observe dust tails, ionized gases, and faint jets that would otherwise be lost in glare. The idea of seeing in shadow is deeply human. It reflects a long tradition in science of building tools that extend perception beyond natural limits. Astronomers do not rely on sharper eyes alone. They rely on ways of shaping light itself, deciding what to block so that something else can be revealed. Artificial eclipses are an example of this philosophy. They do not remove the sun. They acknowledge its dominance and work around it. The sun remains present, powerful, unavoidable, but it is no longer absolute. Silence is also a kind of data. When coronagraph-equipped satellites track a region near the sun and detect nothing, that absence matters. It tells researchers that material density is low, that outgassing is minimal, that certain processes are not occurring at measurable levels. In astronomy, seeing nothing often means learning something specific. For 3i Atlas, these observations serve as continuity rather than spectacle. While Earth-based observatories experience a blind interval, space-based instruments maintain a partial thread of awareness. Not complete coverage, not full certainty, but enough to reduce the size of the unknown. This difference affects how scientists think during the obscured phase. Instead of total blindness, there is partial constraint. Models are not free to drift wildly. They are anchored by sparse but meaningful data points. The object is still behaving within expected physical limits. Numbers whisper more than they speak. The measurements collected during this time are often unremarkable to the casual observer. Small changes in brightness, minor shifts in emission lines, gradual evolution rather than sudden change. But these details accumulate. They form a quiet narrative of stability, of processes unfolding without rupture. There is also a human patience embedded in this work. Engineers and astronomers design instruments years before a specific target appears. They do not know which interstellar object will arrive next or when. They prepare for possibilities rather than events. When a visitor like 3i Atlas passes through, the reward is not excitement but relevance. The fact that satellites can still see is not a triumph over nature. It is a negotiation with it. Limits are acknowledged. Constraints are respected. Within those boundaries, observation continues. As 3i Atlas moves through solar conjunction, the presence of these hidden observers changes the emotional tone of the wait. It is no longer a complete pause. It is a thinning of information, not its disappearance. The universe has not gone silent. It has lowered its voice. This chapter is not about extraordinary vision. It's about continuity under constraint, about maintaining connection when conditions are unfavorable, about building instruments that do not demand perfect circumstances, only workable ones. And when the object emerges fully into view again, these shadowed measurements become part of the story. Quiet confirmations that even in the brightest glare, some eyes remain open, watching patiently, learning without interruption. As 3i Atlas returns from behind the sun, astronomers do not begin by asking what it is. They begin by asking how bright it is. Brightness is the first language small bodies speak after silence. It arrives before chemistry, before structure, before interpretation. It is the simplest measurement and often the most revealing. Under ordinary circumstances, the brightness of a comet-like object follows a predictable pattern as it approaches the sun. As distance decreases, solar energy increases, surface ice is warm, and activity grows. This relationship is usually expressed as a power law. Brightness scales with distance to the sun raised to a negative exponent. For many active objects, that exponent sits near -4. Sometimes slightly less, sometimes slightly more. It reflects a balance between heating, sublimation, and geometry. For 3i Atlas, that balance does not hold. Before solar conjunction, its brightness follows a trend close to R to the -3.8. This is unremarkable. It sits comfortably within expectations. Nothing about it draws special attention. It behaves like an object responding gradually to increasing solar input. Models agree. Observations confirm. The numbers are quiet. Then, after conjunction, the slope changes. The brightness begins increasing closer to R to the -7.5. This is not a small adjustment. It is nearly twice as steep. The object is brightening much faster than distance alone would suggest, not suddenly, not explosively, but persistently across multiple measurements. This is the first true anomaly. Numbers whisper more than they speak. To understand why this matters, it helps to slow down. Brightness is not light emitted by the object itself. It is sunlight reflected and reprocessed by material around it. Dust grains scatter light. Gas fluoresces. The size, quantity, and distribution of that material determine how much light reaches a telescope. A steeper brightness curve means that something about the object's response to solar heating has changed. Either more material is being released, or the released material is more effective at scattering light. Sometimes both. One explanation would be fragmentation. If the object breaks apart, its total surface area increases dramatically, leading to a rapid rise in brightness. But fragmentation usually leaves signatures. Sudden jumps, irregular morphology, multiple condensations, none of these appear. Another possibility is a transition in the dominant volatile driving activity. Different ices respond differently to temperature. Water ice sublimates efficiently closer to the sun. Carbon monoxide and carbon dioxide can drive activity farther out. A shift between these regimes can alter the brightness slope. But even this explanation does not fully account for the steepness observed. Space rarely gives us simple answers. The key insight is that brightness does not scale linearly with mass loss. It scales with effective surface area. If material is released not as a smooth flow but as fine grains, the scattering cross-section increases rapidly. A relatively modest increase in mass loss can produce a disproportionate increase in brightness. This points toward a change in how material is being released, not just how much. After solar conjunction, 3i Atlas appears to expose fresh material. Layers that were previously insulated or chemically altered by interstellar radiation may have been stripped away. What remains is more volatile, more reactive, and more responsive to solar energy. The object is not becoming larger. It is becoming more efficient at interacting with light. This is subtle physics, but it is decisive. The steep brightness slope persists across observing platforms and wavelengths. It is not an artifact of instrumentation. It is not a calibration error. Independent teams see the same trend. The anomaly survives scrutiny. Silence is also a kind of data. What is absent here matters as much as what is present. There is no chaotic variability, no erratic flaring, no evidence of catastrophic mass loss. The brightness increase is smooth, monotonic, almost disciplined. This argues against mechanical failure and in favor of a controlled physical transition. This is why this moment becomes the first pivot in the story of 3I Atlas. Before this, everything fits comfortably within known categories. After this, the object demands a more careful description. It is still behaving according to physics, but not according to the simplest version of it. For the scientists watching, this is a familiar feeling. It is the point where curiosity deepens, not because something is shocking, but because something is precise in an unexpected way. The data do not shout. They lean closer. Brightness curves are often overlooked by the public. They lack imagery. They lack drama. They are lines on a plot, slopes measured over time. But for researchers, they are narratives written in numbers. Numbers whisper more than they speak. In the case of 3I Atlas, the whisper says this: the object has changed internally without losing coherence. Its response to the sun is no longer governed by surface exposure alone. Subsurface processes are now contributing. Energy is being translated into activity through pathways that were previously dormant. This does not make the object exotic. It makes it informative. By the end of this chapter, nothing has been proven. No conclusions are closed. But the tone has shifted. The object is no longer simply surviving. It is revealing structure through behavior. And in that quiet steepening of a curve, you are reminded that in astronomy, the first real mystery often arrives not as a spectacle, but as a deviation so gentle and consistent that it can only mean something deeper has begun to show itself. Water is one of the most familiar substances in astronomy, and yet it is also one of the most carefully constrained. There are places where water is expected, and places where it should remain locked away, frozen and inactive. Distance from the sun matters. Temperature matters. For most small bodies, liquid or actively sublimating water does not belong far from solar warmth. That is why the next set of observations surrounding 3I Atlas quietly alters the tone of the investigation. At a heliocentric distance of about 2.9 astronomical units, nearly 3 times farther from the Sun than Earth, conditions are typically too cold for water ice on a small object to drive significant activity on its own. At this distance, classical comet behavior is usually powered by more volatile compounds, substances like carbon monoxide or carbon dioxide that can sublimate at much lower temperatures. Water ice, by comparison, is expected to remain largely inert, and yet the signatures appear. The detection does not come in the form of glistening ice or vapor clouds. It comes indirectly through chemistry. When water molecules break apart under solar ultraviolet radiation, they produce hydroxyl radicals, known as OH. These radicals emit at specific ultraviolet wavelengths. They are not water itself, but they are its unmistakable fingerprint. This is where the Swift Space Telescope enters the story. Swift is not designed to take picturesque images of comets. Its strength lies in sensitivity and timing. Operating above Earth's atmosphere, it can detect faint ultraviolet emissions that ground-based telescopes struggle to isolate. When Swift turns its instruments toward 3I Atlas, it is not searching for spectacle. It is measuring whether certain wavelengths are present at all. They are. The OH emission is faint but persistent. It appears consistently enough to rule out noise or coincidence. From this signal, astronomers estimate a water production rate of roughly 40 kilograms per second. This is not an enormous amount by cometary standards. It is not a plume. It is not a burst, but it is real. Numbers whisper more than they speak. 40 kilograms per second at nearly 3 astronomical units is not supposed to happen easily. At that distance, solar heating is weak, surface temperatures remain low. For water to be released at this rate, it cannot simply be sitting exposed on the surface. Something else must be enabling it. This is where interpretation becomes careful rather than dramatic. One possibility is that water ice exists beneath an insulating layer and is being released indirectly. If other volatiles sublimate first, they can carry entrained water vapor with them. In this scenario, water is not the primary driver of activity, but a passenger pulled along by more volatile companions. Another possibility is that water ice is present in an unusually fine-grained or porous form, increasing its effective surface area. Even small increases in temperature can then produce measurable sublimation. The physics remains ordinary. The structure is what matters. Space rarely gives us simple answers. What matters most is not the presence of water itself, but the context. This detection aligns with the earlier brightness anomaly. Both suggest that material previously shielded is now participating in activity. The object is not just losing mass, it is revealing layers. There is also an emotional undercurrent to these measurements, though it is rarely stated outright. Water is familiar. It carries associations that go beyond science. In planetary exploration, water often marks transitions, histories, and potential. But here those associations must be restrained. This water does not imply habitability. It does not imply biology. It does not imply intention. It implies exposure. Silence is also a kind of data. Equally important is what Swift does not see. There is no explosive increase in water production as 3I Atlas approaches. There is no runaway behavior. The emission remains modest, controlled, and consistent. This suggests a stable release mechanism rather than a structural failure. The measured rate fits within a narrow window. It is enough to matter, not enough to dominate. That balance is telling. It indicates that water is part of the story, but not the author of it. From a human perspective, this is the moment when interstellar space feels less abstract. Water detected here is not pristine. It has been processed by cosmic radiation, altered over millions of years, and stored in deep cold. Its release now is not a message. It is a consequence. The universe is not offering surprises for attention, it is offering continuity for understanding. For astronomers, this detection strengthens confidence rather than raising alarms. It supports the idea that 3I Atlas is not an outlier behaving wildly, but a coherent object responding to new thermal conditions in a measurable way. The physics remains grounded, the interpretation remains cautious. Numbers whisper more than they speak. By the end of this chapter, the picture has gained texture. 3I Atlas is no longer just brightening. It is chemically active in a way that challenges simple expectations without violating physical law. Water, present where it should be quiet, tells a story of structure, shielding, and gradual exposure. And as the object continues its journey inward, you are left with a quiet realization that even in places where water should sleep, the universe sometimes allows it to speak softly, just enough to be heard by those who know how to listen. When people imagine how a comet becomes active, they often picture a simple process. Sunlight warms the surface, ice turns directly into vapor, gas escapes, dust follows, the object brightens. This picture is not wrong, but it is incomplete. It describes surface sublimation, the most straightforward pathway from cold solid to expanding coma. What it does not describe is how many comets actually behave once their interiors begin to participate. For 3I Atlas, the observations point toward a more layered mechanism, one that unfolds quietly and efficiently rather than dramatically. At the heart of this mechanism is the ice grain, Instead of gas flowing only from exposed surface ice, some comets release material in the form of tiny solid particles, microscopic grains of ice mixed with dust. These grains are lifted from beneath the surface by escaping gas and carried into surrounding space. Once released, they do something subtle but powerful. They increase the effective surface area of the object by orders of magnitude. A single exposed surface can only sublimate so fast. A cloud of grains, each with its own surface, can process solar energy far more efficiently. Numbers whisper more than they speak. This is what scientists mean when they refer to a natural jet mechanism. It is not a focused plume like a rocket exhaust, it is a collective effect. Gas pressure builds beneath a porous or fractured layer. When pathways open, material escapes preferentially along certain directions. Ice grains are entrained in the flow and dispersed outward. Each grain becomes a tiny active site, releasing gas as it absorbs sunlight. The result is a gradual but powerful amplification of activity without requiring structural failure or explosive release. The object remains intact. Its mass loss remains controlled. Yet its brightness and chemical output increase far more rapidly than surface sublimation alone would predict. This distinction matters. Surface sublimation is limited by geometry. Only the sunlit face participates. The rate scales smoothly with temperature. It is predictable, stable, and relatively conservative. Grain-driven activity, by contrast, decouples activity from the original surface area. Once grains are lofted, they continue to contribute even as they move away from the nucleus. Space rarely gives us simple answers. For an interstellar object like 3I Atlas, this mechanism carries additional implications. Its surface has spent millions of years exposed to cosmic radiation, forming a processed, organic-rich crust. Beneath that crust, more volatile material can remain preserved. When solar heating penetrates or fractures this layer, the release is not uniform. It favors channels, it favors jets. Importantly, these jets do not need to be visually dramatic. They can be diffuse, persistent, and subtle. Their presence is inferred not from images, but from changes in brightness slopes, gas production rates, and non-gravitational forces. Silence is also a kind of data. What observers do not see is just as telling. There are no sudden spikes in activity, no chaotic variability, no evidence of fragmentation. The jet mechanism operates steadily as a natural outcome of internal structure and solar input. This steadiness is a clue. It suggests that the object's interior is porous and thermally responsive rather than brittle. From a human standpoint, this mechanism reflects a broader pattern in science. Complex behavior often emerges from simple rules applied repeatedly. Gas escapes, grains lift, surface area grows, energy coupling increases. None of these steps require exotic physics. Together, they produce an outcome that initially appears unexpected. Numbers whisper more than they speak. For 3I Atlas, the jet-driven grain release offers a unifying explanation. It accounts for the steep brightness increase. It aligns with the detection of water at larger distances. It remains consistent with the object's survival through solar passage. It does not require assumptions beyond known cometary physics. The difference is context. This is not a comet shaped entirely by one star. It is a body shaped by interstellar space, now responding to a new environment. Its jet activity reflects a transition from long-term cosmic exposure to short-term solar influence. This is why distinguishing grain-driven jets from simple surface sublimation matters. One implies a passive response. The other implies an internal architecture capable of amplifying change without losing integrity. As the data accumulate, the picture becomes clearer, but not louder. 3I Atlas is not announcing itself. It is demonstrating how structure governs behavior under stress. And in that demonstration, you are reminded that some of the most effective engines in the universe are not designed, not centralized, and not obvious, but emerge quietly when energy meets complexity in just the right way. Color is one of the quietest forms of information in astronomy. It does not announce itself. It does not demand interpretation. It simply shifts slowly as conditions change. For small bodies like 3I Atlas, color is not decoration. It is a record of exposure, chemistry, and depth. When 3I Atlas is first observed far from the Sun, its color is noticeably red. This is not unusual. Many small bodies in the outer regions of planetary systems display red spectral slopes. Over long periods of time, cosmic radiation alters surface materials, breaking molecular bonds and reorganizing carbon-rich compounds into complex organic residues. These processed layers absorb blue light and reflect redder wavelengths. The result is a dark reddish coating, often referred to as an organic mantle. This mantle forms slowly, patiently, in cold and quiet environments. Interstellar space is especially effective at producing it. With no nearby star to refresh the surface, radiation works uninterrupted for millions of years. By the time 3I Atlas enters the solar system, its exterior carries the signature of that long exposure. Then the color begins to change. As the object approaches the Sun and activity increases, its spectral slope flattens. The deep red softens toward neutral. Later still, it shifts further, moving into a faintly blue regime. This progression is measured carefully across multiple wavelengths and instruments. It is not a trick of lighting. It is not an observational artifact. It is a physical transformation unfolding in real time. Numbers whisper more than they speak. A blue-ward shift in color tells you something specific. It suggests the increasing presence of small particles and gas that scatter shorter wavelengths more efficiently. Fine dust grains, especially those freshly released, tend to reflect blue light more strongly. Certain gases emit in the blue and near ultraviolet. The combined effect alters the object's overall color. But color alone is only the surface of the story. The deeper meaning lies in which materials are being exposed. Spectroscopic observations reveal increasing contributions from carbon monoxide and nitrogen-bearing compounds, including amides. These molecules are not typically dominant in the most processed outer layers. They are more abundant beneath the radiation-altered crust. Their appearance signals that material from deeper regions is now participating in activity. Space rarely gives us simple answers. Carbon monoxide is especially telling. It sublimates at much lower temperatures than water ice. Its presence indicates that volatile rich layers, long preserved in cold storage, are now accessible. Amide compounds add another layer of context. They are part of a broader family of complex organics, often formed or modified by radiation chemistry. Seeing them change in relative abundance suggests that the balance between surface residue and interior material is shifting. This is not the creation of new material. It is the exposure of old material. The red mantle does not disappear all at once. It is thinned, disrupted, and partially removed by ongoing activity. Gas flow lifts dust and ice grains away. Jets preferentially erode weaker regions. Over time, the outermost layer gives way, revealing a composition that has been hidden for most of the object's history. Silence is also a kind of data. What is not observed matters here as well. There is no sudden collapse of the surface, no violent shedding of an entire layer. The transition is gradual, consistent with erosion rather than destruction. This reinforces the picture of a structurally coherent object undergoing controlled exposure. For scientists, this color evolution is one of the most informative aspects of 3I Atlas. It provides a rare opportunity to watch an interstellar object adjust chemically as it encounters a new environment. Most objects shaped by our Sun have already gone through this process long ago. Their surfaces have equilibrated, their colors have stabilized. 3i Atlas is different not because it is exotic, but because it is early. From a human perspective, there is something quietly familiar about this process. Layers built over time are not removed by force, but by persistence. Exposure does not require violence. It requires patience and energy applied steadily. Numbers whisper more than they speak. The shift from red to blue does not mean the object is becoming simpler. It means it is becoming more legible. Each color corresponds to a layer, a history, a chemical regime. As those layers are peeled back, interpretation becomes possible. Importantly, none of this implies intention or design. The chemistry follows known rules. Radiation modifies surfaces, heat mobilizes volatiles, gas flow redistributes material. The outcome looks complex because the history is long, not because the physics is strange. By the end of this chapter, the image of 3i Atlas has gained depth. It is no longer a uniformly processed relic drifting unchanged from another star. It is an object with internal variation, now revealing that variation through interaction with sunlight. Color in this context is not beauty, it is evidence. And as the spectrum shifts quietly from red toward blue, you are reminded that understanding often comes not from what suddenly appears, but from what slowly becomes visible when outer layers finally let the light through. The encounter with Mars is not a collision, not an interception, and not a rendezvous in any human sense. It is a flyby, distant and quiet, measured in astronomical units rather than kilometers. Yet for astronomy, it marks something that has never happened before. As 3i Atlas continues its passage through the inner solar system, its trajectory brings it within about 0.99 astronomical units of Mars. This is not close by everyday standards. It is still tens of millions of kilometers away. But in planetary terms, it is an alignment that matters. It places an interstellar object within observational reach of a robotic observer standing on the surface of another planet. For the first time in history, a visitor from another star system passes near enough to Mars to be observed not only from Earth and space, but from the ground of a different world. This matters less because of proximity and more because of perspective. Mars is not just another vantage point. It is an environment with its own sky, its own dust, its own atmospheric filtering. Instruments operating there experience a different noise profile, a different geometry, and a different background. Observations from Mars do not replace those from Earth. They complement them, adding a layer of triangulation that astronomy rarely gets. At the center of this moment is the Perseverance rover. Perseverance was not designed to study interstellar objects. Its mission is geological, chemical, and planetary. It looks at rocks, sediments, and ancient environments. But it also carries cameras and sensors capable of tracking the sky, measuring light, and detecting motion against the Martian atmosphere. When timing and geometry align, those instruments can be repurposed, briefly, for something else. Numbers whisper more than they speak. The flyby distance of 0.99 AU is close enough that 3i Atlas appears slightly brighter from Mars than from Earth at the same time. The phase angle is different. The scattering geometry changes. These small differences matter. They allow scientists to cross-check brightness models and activity estimates in a way that would otherwise be impossible. This is not about seeing more detail. It is about seeing the same thing under different conditions. Space rarely gives us simple answers. From Perseverance's position, the sky is thinner, dustier, and more variable. Mars has its own weather, its own scattering effects. Any detection of 3-eye Atlas must account for that. But if a signal is seen and matches predictions, it strengthens confidence in interpretation. If it deviates, it invites careful reconsideration. Even the attempt itself is informative. Whether Perseverance detects the object clearly or only marginally, the effort expands the observational footprint of humanity. It demonstrates that planetary missions are not isolated endeavors. They are part of a growing, distributed network of sensors spread across worlds. Silence is also a kind of data. If the rover sees nothing, that absence constrains brightness limits. It tells scientists how faint the object truly is at that geometry. If it sees something, even faintly, it confirms models built from Earth-based and orbital observations. Either outcome contributes. What is remarkable here is not technological triumph, but timing. Perseverance is on Mars now. 3-eye Atlas is passing now. The overlap is not planned, it is coincidental. Astronomy often advances through such coincidences, moments when preparation meets opportunity without ceremony. From a human standpoint, there is something quietly grounding about this. A machine built to study ancient Martian riverbeds pauses briefly to look outward. It becomes a witness not just to planetary history, but to interstellar motion. The scale shifts, but the method remains the same. Observe carefully. Compare. Infer. Numbers whisper more than they speak. This flyby also reframes how interstellar objects are understood. They are no longer distant curiosities glimpsed only from Earth. They are participants in a multi-planet observational context. Each new vantage point reduces ambiguity, not by adding spectacle, but by adding constraint. The phrase "first in history" applies here in a precise way. It is not the first time an interstellar object enters the solar system. It is not the first time one is studied. It is the first time one passes close enough to another planet for that planet to become an observing platform. That distinction matters. As 3-eye Atlas moves past Mars and continues inward, the opportunity closes as quietly as it opened. The geometry shifts, the window narrows. Perseverance returns its focus to the ground beneath its wheels. But something has changed. Interstellar space has briefly intersected with planetary exploration. Two threads of astronomy, often separate, have crossed without announcement. No signal is sent. No message is received. Only measurements are exchanged. And in that quiet crossing, you are reminded that discovery does not always arrive as a revelation, but sometimes as alignment, when different paths happen to overlap just long enough for understanding to deepen before moving on again. As 3-eye Atlas approaches perihelion, attention shifts quietly but decisively. This is the region where small bodies are tested most severely. Solar radiation intensifies. Thermal gradients steepen. Internal stresses rise. For objects with unknown structure, this is where uncertainty concentrates. The concern is not dramatic failure. It is fragmentation by accumulation, tiny cracks expanding, volatiles escaping unevenly, material weakening over time. In cometary science, many objects do not survive this passage intact. Some split into multiple components, some shed mass so rapidly that their identity changes, some simply fade, leaving behind diffuse remnants that no longer behave as coherent bodies. For an interstellar object like 3-eye Atlas, these concerns are sharpened by ignorance. Its internal composition is inferred, not known. Its mechanical strength is estimated, not measured. Its history spans environments unlike those of typical solar system comets. Models must extrapolate beyond familiar ground. Space rarely gives us simple answers. The hypothesis of breakup is therefore reasonable. As 3-eye Atlas draws closer to the Sun, increasing activity could undermine structural integrity. Jets might excavate weak regions. Differential heating could introduce stress between layers formed under different conditions. Mass loss could accelerate in a feedback loop, exposing deeper material faster than the object can respond. From a distance, these processes are difficult to separate from one another. Brightness changes can mimic fragmentation. Dust production can obscure the nucleus. Apparent changes in shape can result from viewing geometry rather than physical alteration. Numbers whisper more than they speak. Astronomers approach this phase with caution rather than expectation. They track brightness continuity. They monitor morphology. They compare positions against predicted orbits. Fragmentation, if it occurs, leaves signatures. Multiple condensations appear. The trajectory deviates subtly. The coma becomes asymmetric in ways that persist. At the same time, mass loss itself is not a sign of failure. Comets lose mass continuously. The question is not whether 3I Atlas is losing material, but how. A steady, controlled loss indicates resilience. A sudden, uneven loss raises concern. Silence is also a kind of data. As perihelion passes, observations resume and accumulate. The object is still there. The position matches prediction. The brightness evolves smoothly rather than erratically. No secondary nuclei appear. No sudden dispersal is detected. The nucleus remains coherent. This confirmation does not arrive as a single announcement. It emerges gradually as each new data point aligns with the previous ones. The fear of breakup recedes not because it was unfounded, but because it is not supported by evidence. Mass loss is present, it is measurable, it is expected, but it is not catastrophic. Estimates indicate material is being shed at rates consistent with sustained activity, not collapse. The object is changing, but it is not failing. For researchers, this outcome is quietly significant. Survival through perihelion constrains internal structure. It implies a degree of cohesion, a balance between porosity and strength. It suggests that the interior can accommodate gas flow without tearing itself apart. From a human perspective, there is a subtle shift here. Anticipation gives way to recalibration. The object is no longer just enduring passage. It is demonstrating capacity. Space rarely gives us simple answers. The absence of breakup is not the absence of change. The surface has been altered. Layers have been eroded. Volatiles have been mobilized. But the core remains intact. This distinction matters because it allows the story to continue. Post-perihelion behavior can now be interpreted as evolution rather than aftermath. Numbers whisper more than they speak. Brightness curves remain smooth. Orbital deviations stay within modeled limits. The physical narrative remains coherent. Each of these quiet confirmations strengthens confidence in earlier interpretations. The grain-driven activity, the chemical exposure, the controlled response to solar heating, all of these pieces fit more tightly together now. The fear of disintegration was never about spectacle. It was about losing access to information. A fragmented object becomes harder to interpret. Processes overlap. Signals blur. Survival preserves clarity. As 3I Atlas moves away from the Sun, the most intense thermal stress has passed. The object carries the imprint of that encounter, but not its scars. What remains is a body that has been tested and found resilient, at least within the limits observed. This chapter does not close with relief. It closes with quiet affirmation. The universe did not behave unexpectedly. It behaved consistently, under conditions that demanded careful attention. And in that consistency, you are reminded that endurance in space is rarely dramatic, but often decisive, revealing not what breaks under pressure, but what continues, altered yet intact. into the next stretch of its long journey. As 3i Atlas continues its journey through the inner solar system, the story begins to shift from what is visible to what is measurable. At this stage, astronomers are no longer focused on brightness alone. They are watching motion itself, not the broad sweep of the orbit, which remains dominated by gravity, but the small deviations layered on top of it. These deviations are subtle, persistent, and informative. The first indication comes from trajectory analysis. When the object's position is compared carefully against purely gravitational models, a slight discrepancy appears. The path does not diverge dramatically. It drifts. The difference accumulates slowly over time, measurable only through precise tracking across many observations. This is what astronomers call non-gravitational acceleration. It does not imply an external force. It does not imply control or intention. It refers to any acceleration not explained by gravity alone. In the context of comets, the most common cause is outgassing. When material escapes asymmetrically from the nucleus, it produces a reaction force, small but continuous. Numbers whisper more than they speak. In the case of 3i Atlas, the direction of this acceleration matters. Analysis indicates a component directed sunward toward the Sun, rather than away from it. At first glance, this can seem counterintuitive. One might expect escaping gas to push the object away from the Sun, like exhaust from a warming surface. But cometary physics is more subtle than that. Space rarely gives us simple answers. A sunward jet does not mean material is flowing toward the Sun. It means that gas is escaping from regions oriented away from the Sun, producing a recoil that nudges the nucleus inward. This geometry arises naturally when activity is localized rather than uniform. If a jet emerges from the night side or from regions shielded from direct sunlight, the net force can point sunward. Thermal lag plays a role here. Materials do not heat and cool instantaneously. As the object rotates, regions that were previously sunlit can continue releasing gas even after moving into shadow. This delayed response shifts the direction of net thrust. The result is a force that does not align neatly with the Sun-object line. Silence is also a kind of data. What matters is not the presence of non-gravitational acceleration, but its magnitude and stability. In 3i Atlas, the acceleration is modest. It evolves smoothly. It fits within ranges observed for active comets in our own solar system. There are no abrupt changes that would suggest structural instability or exotic processes. This alignment reinforces earlier interpretations. Grain-driven jets, volatile release from subsurface layers, and gradual erosion all contribute to an asymmetric outflow pattern. The physics remains familiar. The context is new. From a human perspective, this is a moment of interpretive discipline. Non-gravitational forces have, in the past, been used to fuel speculation when context is ignored. Here, context is everything. The observed acceleration aligns with measured activity. It scales with distance. It correlates with brightness changes. It behaves as expected. Numbers whisper more than they speak. Astronomers model these forces using parameters refined over decades of comet study. They adjust outgassing coefficients, incorporate rotation states, and test different jet configurations. The goal is not to fit the data at any cost, but to see whether standard models suffice. They do. The sunward component does not require new physics. It does not require unfamiliar mechanisms. It emerges naturally from known comet behavior under asymmetric activity. The fact that it appears in an interstellar object is notable, but not disruptive. Space rarely gives us simple answers. There is also significance in what is absent. No erratic acceleration spikes, no unexplained directional flips, no signs of thrust inconsistent with mass loss estimates. These absences narrow the range of plausible interpretations. They reinforce the conclusion that 3I Atlas is behaving like a coherent, active small body, responding to solar input. For those watching closely, this moment serves as a grounding point. Motion, measured precisely, acts as a cross-check on everything else. Brightness, chemistry, and structure must all be consistent with the observed trajectory. In this case, they are. The object continues along its path, slightly nudged, subtly adjusted, never dramatically redirected. Gravity still dominates. Outgassing merely adds a gentle correction. By now, a pattern is clear. Each new layer of data does not overturn the previous one. It supports it. The story remains cohesive, not because it is simple, but because it is constrained. And in that quiet sunward drift, you are reminded that in space, even the smallest forces leave traces, and when those traces align, they tell a story not of mystery, but of understanding unfolding at its own unhurried pace. By the time 3I Atlas has revealed changes in brightness, chemistry, and motion, one question still lingers quietly at the edges of discussion. Is the water real, or is it inferred only indirectly? In astronomy, indirect evidence is often enough, but confirmation through an independent channel carries special weight. That confirmation arrives not through light, but through radio waves. Radio astronomy listens where optical telescopes cannot see. It does not rely on reflected sunlight or glowing dust. It listens for specific frequencies emitted by molecules as they change energy states. These signals are precise. They are difficult to imitate, and when they appear, they speak clearly about composition. This is where the Meerkat radio telescope enters the picture. Meerkat is an array of dozens of dishes spread across the landscape of South Africa, working together as a single, sensitive instrument. Its strength lies not in dramatic images, but in its ability to detect faint, narrow-band signals across vast distances. When it turns toward 3I Atlas, it is not searching for the object itself. It is listening for a molecular signature. That signature appears at frequencies between 1665 and 1667 MHz. These frequencies are well known to astronomers. They correspond to emission from hydroxyl radicals, the same OH fragments previously inferred from ultraviolet observations. In radio wavelengths, these transitions are especially valuable because they are unambiguous. They arise from specific quantum processes. There is no confusion about their origin. Numbers whisper more than they speak. The detection of OH emission at these frequencies provides direct radio evidence of water production. It confirms that water molecules are being broken apart by solar radiation, producing hydroxyl radicals that emit at precisely these wavelengths. This is not a model-dependent inference, it is a measurement. Importantly, the signal strength and line shape are consistent with natural cometary outgassing. The emission is broad, not narrow. It varies smoothly with time. It shows none of the hallmarks of artificial transmission, which would require coherence, modulation, or repetition inconsistent with molecular physics. Space rarely gives us simple answers. But here, the answer is simple enough. Radio detection closes a loop. Ultraviolet observations suggest water through secondary chemistry. Brightness behavior supports ongoing activity. Now radio measurements independently confirm the presence of water-derived molecules. 3 different observational channels converge on the same conclusion. Silence is also a kind of data. What Meerkat does not detect matters as much as what it does. There are no unexplained signals, no anomalous narrow-band spikes, no structured transmissions. The radio environment around 3I Atlas is quiet, except for the expected molecular emissions. This absence of irregularity constrains interpretation strongly. In science, hypotheses are not dismissed by opinion. They are narrowed by evidence. Early speculation about artificial origins thrives in gaps, in places where data are sparse. As measurements accumulate, those gaps close. Radio observations are especially effective at doing this because artificial signals, if present, would be difficult to hide at these frequencies. Numbers whisper more than they speak. The Meerkat data show line ratios and temporal behavior that match known cometary OH emission. The signal strength aligns with water production rates inferred from other methods. There is no excess energy, no unexplained power source. Everything balances. From a human perspective, there is a quiet satisfaction in this kind of confirmation. It does not arrive as a revelation. It arrives as alignment. Different tools built for different purposes, all pointing toward the same physical explanation. This is how uncertainty dissolves in astronomy. Not through decisive moments, but through convergence. Space rarely gives us simple answers. The phrase "end of the artificial hypothesis" does not mean an idea has been defeated. It means it is no longer needed. Natural explanations account for the observations fully and consistently. When a simpler, well-tested framework explains the data, adding complexity no longer adds understanding. What remains is not disappointment but clarity. 3i. Atlas is not an engineered object emitting signals. It is a natural body releasing water, responding to solar energy, and behaving according to known physical laws. Its interest lies not in intention, but in history, not in design, but in exposure. As the radio waves fade back into background noise and the object continues its path, the universe offers a reminder that mystery does not disappear when explanations succeed. It simply moves to a deeper level, where understanding replaces speculation and curiosity continues, grounded, patient, and open. For a long time, interstellar objects were imagined as pristine. Untouched fragments drifting between stars, preserved in deep cold, carrying the original chemistry of their birth systems. This idea is intuitive. Distance feels like protection. Isolation feels like preservation. But 3i Atlas slowly, quietly dismantles that assumption. One of the most telling measurements comes from a simple ratio: the relative abundance of carbon dioxide to water. For 3i Atlas, that ratio is approximately 7.6. This number does not announce itself. It sits in a table. It waits to be compared. In many solar system comets, water dominates once they approach the sun. Carbon dioxide contributes, but it rarely overwhelms. A ratio this high immediately signals that something is different. Either water has been depleted, carbon dioxide has been enhanced, or both. None of these possibilities are neutral. Each points to long-term processing. Numbers whisper more than they speak. Carbon dioxide is more volatile than water, but less volatile than carbon monoxide. Its presence at this level suggests that the object's near-surface layers are not simply frozen snapshots of formation. They have been altered. The balance of volatiles has shifted. To understand why, you have to step away from the sun entirely and think about time. Interstellar space is not empty. It is quiet, but it is active in its own way. High-energy cosmic rays permeate it. These particles travel at nearly the speed of light, penetrating meters into solid material over long periods. Unlike solar radiation, which comes from one direction and varies with distance, cosmic radiation is relentless and isotropic. It arrives from all directions, without pause. Over millions of years, this exposure matters. Cosmic rays break molecular bonds. They rearrange chemistry. They drive reactions that would never occur at low temperatures alone. Water molecules can be dissociated. Carbon-bearing compounds can polymerize. New structures form, not because energy is abundant, but because time is. Space rarely gives us simple answers. The result of this exposure is a processed outer layer, not melted, not burned, but altered, chemically transformed in slow motion. This is what scientists refer to, informally, as a cooked crust. The term is not poetic. It reflects cumulative energy deposition, not heat in the everyday sense. This crust acts as both shield and record. It protects deeper material from further radiation, while preserving the history of exposure on its surface. Underneath, more pristine ices may still exist, but they are no longer the first material to interact with a star. For 3I Atlas, the high CO2 to water ratio suggests that water in the near-surface region has been preferentially lost or transformed. Cosmic radiation can break water into hydrogen and oxygen. Hydrogen escapes easily. Oxygen reacts with carbon-rich material. Over time, this process favors carbon oxides relative to water. Silence is also a kind of data. Equally important is what is not seen. There is no overwhelming dominance of carbon monoxide at this stage, which would indicate extremely pristine material. There is no absence of water either, which would suggest complete depletion. The chemistry sits in between, altered but not erased. This intermediate state is the signature of long residence in interstellar space, long enough to be processed, not so long that structure is lost. From a human perspective, this challenges a comforting idea. That distance preserves, that untouched means original. In reality, isolation exposes material to a different kind of influence, one that works slowly but persistently. Numbers whisper more than they speak. The cooked crust of 3I Atlas also explains earlier observations. Why fresh material appears only after solar heating increases. Why color shifts reveal deeper layers gradually. Why activity does not begin explosively. The crust regulates access, controlling when and how volatiles are released. This is not a fragile object. It is a layered one, calling 3I Atlas. A non-primitive comet does not diminish its value, it increases it. It becomes a record not just of formation, but of survival. It tells you what happens to small bodies that wander between stars for geological timescales. In solar system science, many comets have already lost their original surfaces. They have been heated repeatedly. Their histories are compressed. 3I Atlas offers something different. A long, uninterrupted exposure to the interstellar environment, now briefly illuminated by a star. Space rarely gives us simple answers. The object is not a messenger from a distant system frozen in time. It is a traveler that has been shaped by the journey itself. Its chemistry reflects motion, not origin alone. Its surface tells you where it has been, not just where it came from. By the end of this chapter, the picture is clearer and quieter. Interstellar objects are not pristine archives. They are evolving records. They carry the marks of radiation, time, and absence. And in that realization, you are left with a calm shift in perspective, that what survives the longest in the universe is rarely what remains unchanged, but what adapts slowly, layer by layer, to conditions no one ever intended it to endure. By the time the chemical layers of 3I Atlas begin to make sense, attention turns inward, not toward composition alone, but toward energy. Small bodies are often treated as passive. They warm, they cool, they respond. But sometimes, under the right conditions, they also participate. One of the more subtle clues comes from the detection of metals, specifically nickel and iron. These elements are not unexpected in small bodies. They are common in planetary materials. What matters is how they appear, and what they can do when exposed. Nickel and iron are chemically active in ways that ice and dust are not. When fresh metallic grains come into contact with certain volatiles, especially water and carbon-bearing compounds, reactions can occur. These reactions do not require high temperatures. They require proximity, time, and a release pathway. Numbers whisper more than they speak. Laboratory studies have shown that finely divided metal grains can catalyze exothermic reactions when exposed to water vapor. Energy is released quietly, locally, and repeatedly. Not enough to melt an object, not enough to fracture it, but enough to alter thermal balance in small regions. In an object like 3I Atlas, this matters. As the processed outer crust thins and subsurface material becomes accessible, metallic grains that were once isolated may now interact with volatiles for the first time in millions of years. The result is not combustion in any familiar sense. It is localized heating, gentle but persistent, occurring below the surface. Space rarely gives us simple answers. This internal heat does not behave like solar heating. It is not directional. It does not depend on illumination. It can operate in shadowed regions, beneath insulating layers. It adds complexity to the thermal picture without dominating it. One possible outcome of this process is cryovolcanism. Cryovolcanism is often associated with icy moons, where internal heat drives the eruption of water, ammonia, or other volatiles instead of molten rock. In small bodies, the scale is different, but the principle is similar. Pressurized pockets of volatile-rich material can be mobilized by internal heating and released through fractures or porous channels. In this context, cryovolcanism does not mean towering plumes or surface collapse. It means episodic release, small jets, enhanced activity from specific regions, behavior that appears organized without being violent. Silence is also a kind of data. What observers see in 3I Atlas is consistent with this restrained version of cryovolcanic behavior. Activity persists even when solar heating alone would suggest decline. Jets appear stable rather than chaotic. Gas release remains localized. There is no sign of runaway thermal failure. The presence of nickel and iron provides a plausible energy source for this behavior, one that operates quietly alongside solar input. It does not replace external heating. It supplements it, smoothing transitions and extending activity. From a human perspective, this is a reminder that energy does not need to be abundant to be influential. Small amounts, applied consistently in the right context, can shape outcomes over long periods. Numbers whisper more than they speak. Importantly, none of this requires speculative mechanisms. Exothermic reactions involving metals and volatiles are well documented. Cryovolcanism is observed elsewhere in the solar system. What is new is the setting. An interstellar object long processed by radiation, now briefly energized by a star, revealing internal pathways that were dormant for most of its existence. This synthesis helps explain lingering questions: why activity remains structured, why mass loss is controlled, why the object survives thermal stress. Internal heat provides flexibility. It allows gas to escape without tearing the structure apart. Space rarely gives us simple answers. Calling this cryovolcanism does not imply drama. It implies continuity. It is a slow conversation between chemistry and physics, conducted beneath the surface, expressed only through subtle changes in behavior. As 3I Atlas continues on its way, these processes fade back into dormancy. Solar heating decreases, volatile mobility declines, internal reactions slow. The object returns to a quieter state, carrying with it the imprint of this brief awakening. This final chapter does not close the story, it reframes it. 3I! Atlas is not just a cold fragment warmed from the outside. It is a layered system capable of modest internal activity when conditions allow. Its behavior emerges from interaction, not design. from material properties, not intention. And in that understanding, you are left with a calm recognition that even the smallest travelers in the universe can carry hidden sources of change, waiting patiently for the right moment to speak, softly, through motion, chemistry, and time. As this chapter of observation comes to a close, 3i Atlas is already moving on. Its path carries it away from the inner solar system, back toward the quieter distances where sunlight weakens and activity slowly subsides. The brief window of intense interaction is ending, not with a conclusion, but with a transition. Before it fades completely from practical reach, there is one more encounter ahead. In March of 2026, 3i Atlas will pass near Jupiter. The distance will not be intimate, but it will be close enough to matter. If geometry and timing align, the Juno spacecraft may be able to observe it, adding yet another perspective to a journey already marked by rare vantage points. A visitor from another star, passing through the domain of a gas giant, briefly illuminated by instruments designed for something else. What remains is not a list of answers, but a reshaped understanding. 3i. Atlas has shown that interstellar space is not chemically empty. It processes matter continuously, quietly, over immense spans of time. It has shown that small bodies can carry complex natural engines, driven by structure, chemistry, and modest internal energy rather than simple surface heating. And it has shown that we were mistaken to imagine interstellar objects as pristine relics, frozen and unchanged since formation. Numbers whisper more than they speak. The lesson is not that 3i Atlas is extraordinary. It may not be. It may be entirely typical of what wanders between stars. What is different now is not the object but us. For the first time, our instruments are sensitive enough, coordinated enough, and patient enough to follow such an object through change rather than glimpses. Space rarely gives us simple answers. It is possible that 3i Atlas is only the first example we can truly understand. It is equally possible that the next interstellar visitors will feel even more unfamiliar, not because they are designed or intelligent, but because they have spent far longer in environments we are only beginning to measure. And as this object slips back into the darkness between stars, it leaves behind a quiet reminder that the universe does not become less mysterious as we learn more. It becomes deeper, inviting understanding not through spectacle, but through attention, restraint, and the willingness to listen to what time and matter reveal when nothing is trying to be seen.